We will today discuss a property of metric spaces or certain subsets of metric spaces. It is a very important property known as compactness. Okay. As usual, we shall define what is meant by saying that a set is compact and see certain examples of compact sets and some properties of compact sets and also properties of continuous functions defined on compact sets. That is the idea, and compactness is supposed to be next best thing to be a finite set. Okay. So whatever we expect about a finite set with small modifications, so those things are also true in case of compact sets. In this case I would like to point out one very interesting article. I will just give a reference to that article. This author is E. Hewitt. Role of compactness in analysis. Compactness in analysis. It is appeared in a journal called American Mathematical Monthly. Monthly is a volume number 67, year is 1916 and pages 499 to 516. Okay. I do not remember whether I have mentioned about this journal earlier or not. American Mathematical Monthly, that is a very good journal. It contains articles which are based on the BSc or MSc level mathematics. So anybody with that is, you can understand most of the articles, and another interesting part of that is it contains a section called problems section. It gives some problems whose solutions are not known or some problems which are solutions are known, and it invites the readers to submit the solutions. They are given some address and you can send the solutions to that, and after receiving solutions from the readers they publish the best solution and also publish the names of the other people who have solved it. Okay. So that is quite an interesting thing. Okay. Coming back to our this idea of compactness, let us again as usual start with some metric space XD, a metric space, and we take some subset A of X and we will define what is meant by saying that this subset A is compact. Okay. Now to do that we need some ideas. Okay. First of all we shall define what is meant by saying what is an open cover, open cover of A. Okay. In general a cover simply means a family of subsets whose union contains A. Okay. Any cover of A is nothing but a family of subsets of X whose union contains A, and open cover means a family of open subsets. Okay. That is, open cover of A is nothing but a family, let us say, suppose I call each element in that family as G suffix I, say small I belongs to some big I, where big I is some indexing set. Okay. Okay, a family Gi. So what is the property of this family? First of all, each Gi is open and A is contained in union Gi. A is contained in union Gi. So again to repeat, what is an open cover? It is a family of open sets whose union contains A. Okay. Such a thing is called an open cover of A. Okay. Alright. Now when do we say that A is compact? Of course there are many equivalent definitions. The one which we shall use, I am giving it now. It is that every open cover should have every open cover of A should have a finite subcover. Subcover means subfamily. Okay. Subcover means subfamily. So given any such open cover, you should be able to find a finite number of subsets here such that that finite union should contain A. Okay. that finite union should contain A. So that is the definition. Okay. So A is said to be compact if every open cover of A, has a finite subcover. Okay. That means if you can cover A by some family of open sets, then that family of open sets should contain a finite subfamily such that that finite subfamily should contain should cover A. Okay. Of course, remember we are not saying that A should be covered by some finite number of open sets, that will always be true because we can always take X, okay, and X contains A. So this is just one set which contains A. So that is not the idea. Okay. What the idea is that whenever any family of open set covers A, okay, that family should have a finite subfamily which should cover A. Okay. Alright. Now what are the obvious examples of sets satisfying this property? Okay, let us take start from very trivial things. If A is an empty set, this will always happen, right? Okay, you take any one of those sets, that will cover A. Okay. If A contains just one point, then well, if A is contained in the union, that one point should contain at least in one of those. So you just take that set, that will be cover for A. Okay, and proceeding like this, we can say that if A is finite, okay, then suppose A is, let us say A1, A2, An, okay, then A1 is contained in some G1, A2 belongs to some G2, etc. You just take those G1, G2, Gn, okay, their union will cover A. So what is obvious is that every finite set is compact. Okay, every finite set is compact. So that is the first observation that we can make. Okay, every finite subset of X is compact. So that is why I said that compactness is the next best thing to finiteness. In fact, that point is made very clearly in this article. Okay, you can read this article sometime whenever you are free. Okay. Of course, if those were the only examples of compact sets, then this idea would not have been worth studying. There are many examples of infinite sets which are also compact, and we shall see those examples in due course. But before proceeding that, we can also mention one thing. If XD is a discrete metric space, okay, then those are the only examples of compact sets. Okay. As I said, discrete metric space, its main use is to understand the concepts. Okay. Sometimes whenever we define something, we intuitively feel something about that definition, and whether that intuitive feeling is correct or not can be checked by looking at the discrete metric space. Okay. So let us say suppose now XD is a discrete metric space. Okay. Suppose XD is a discrete metric space. Okay. Then suppose I take a subset A of X. Suppose I take a subset A of X. Okay. Then what I want to say is the following. Okay. Then A is compact if and only if A is finite. Of course, this way is true in any metric space. If A is finite, then A is compact, that we have observed already. Okay, that part is true in any metric space. What we want to say further is that in a discrete metric space, those are the only possible examples of compact sets. In other words, in discrete metric space, A is compact implies A is finite. Okay, all right. How does one prove this? That is how will we prove this part? A in a discrete metric space, A is compact implies A is finite. remember we have already observed that in a discrete metric space every set is open, okay, every subset is open. So in particular I can say that every singleton set is also open set. So we can always say that A is, I can always write A as union of these singleton sets, okay, union of singleton sets where you take, okay, or in other words suppose you take this family A belonging to A, okay, this is an open cover for A, right, this is an open cover for A. Okay, and this open cover must have a finite subcover. If A is compact, this open cover must have a finite subcover. That means what? That means there must exist a finite number of these sets whose union covers A, right, but these sets are singleton, okay, so that means a finite number of singleton sets should cover A, right, that means A must be finite, okay. And where will this proof fail? In an arbitrary metric space, because in an arbitrary metric space, I mean this is still a cover of A but not open cover, okay, because these sets may not be open in an arbitrary metric space, okay, alright. Then of course that again leads to a question, okay fine, then what are the examples of compact sets in other metric spaces, okay, okay, we shall answer that question in due course. But before proceeding to other things, let us also observe one more thing, okay. Compactness is one concept which in a certain sense does not depend on which metric space you are thinking about, okay. For example, suppose I take a situation like this, let us say A is contained in Y and Y is contained in X, right, then we have seen that Y can be itself regarded as a metric space, right. Now when I talk of A as a subset of Y and A as a subset of X, okay, right, of course if you take A as a subset of Y and A as a subset of X, the meaning of open covers will change, okay, right. For example, when you say some Gi is an open cover of A, that if you regard A as a subset of Y, then each of these Gi's are open subsets of Y, okay. On the other hand, if you regard A as a subset of X, then each of those Gi's are open subsets of X, okay, and it can happen that a set is open in Y but not open in X, etc., and we have seen that these two things are different, okay, and we have also seen what is the relationship between these two things, okay. For example, Y itself is always open in Y, okay, but it did not be open in X, okay, but what we will show is that in case of compactness that difference does not exist. Whether you regard A is compact regarded as a subset of Y, if and only if A is compact regarded as a subset of X. So in that sense this space X really does not matter when you are talking about the compactness of A, okay. So let me just write this as a theorem, okay, then A is compact, we shall simply say A is compact in X. Compact in X means compact regarded as a subset of X, okay, if and only if A is compact in Y. And after proving this theorem, now we can simply talk of a compact set without bothering about where exactly that set lies, okay. And so we can then sort of assume that we can just talk of the metric space itself as compact, okay. You can say that for example, saying that a metric space is open or a metric space is closed does not make any sense, because X is always open in X, okay, or X is always closed in X, okay, but X may not be compact in X, okay. That is totally different notation, okay. Alright, let us first see how we can prove this, okay. And to do this we basically remember one old characterization of open sets, what we have said is that if you take a subset G of Y, then G is open in Y if and only if G is Y intersection some open set in X, okay. G is Y intersection some open set in X. In fact, basically that is the characterization that we shall use, okay. So let us say, suppose A is compact, let us say we want to prove this way, okay. Suppose A is compact in X, okay. Then we want to prove that A is compact in Y, okay. A is compact in Y, okay. So to show that A is compact in Y, we should consider some open cover of A in Y, okay. So let us say that let us say I call that open cover, let us say HI, let us say HI, I belonging to I, B, and open cover of A in Y. Now what is the meaning of that? It means that A is contained in the union of HI and each HI is open in Y, right, okay. That means the two things, first thing is that A is contained in union of HI, okay, and each HI is open in Y, okay. Alright. Now if each HI is open in Y, what does this mean? HI is open in Y means HI is Y intersection some open set in X, okay. That is what we have seen already, okay. Every open set in Y is an intersection of Y with some open sets in some open set in G. So that means since HI is open in Y, this implies that HI is equal to Y intersection GI, okay. HI is equal to Y intersection GI for some open set GI in X, okay. Alright. Now what we can observe from here is that since A is contained in HI, that means A is contained in Y intersection GI, okay. A is contained in Y intersection GI, but A is already contained in Y, okay, okay. So these two things will imply that A is contained in union of GI, I belonging to I, okay, right. So this part will imply, that is these two things will imply, that is A is contained in union HI and each HI is Y intersection GI, that will imply that A is contained in the union of GI. Is that clear? Okay. But each GI is open in X, that means this is an open cover of A, okay. That is this means GI, I belonging to I, is an open cover of A. Okay, but we have assumed that A is compact in X, okay. We have assumed that A is compact in X, so every open cover of A must have a finite subcover, okay. So since A is compact in X, this open cover has a finite subcover, okay. This open cover has a finite subcover. What does it mean? That there exist a finitely many subsets here, let us say GI1, GI2 etc., such that A is contained in the union of those finite number of subsets, okay. So I can say that suppose since A is compact in X, there exists some indices, suppose I call say I1, I2 etc., suppose there are n of them, In in I, such that A is contained in union of sets corresponding to these particular indices, okay, AI1, AI2 etc., okay. So let us say that A is contained in union of, let us say, GIK, K going from 1 to n, okay. again we use the fact that Gik is nothing but y intersection sorry G A is okay, A is fine, we will come to that later. A is contained in Gik, A is contained in union of Gik, okay, but A is also contained in Y, A is a subset of Y, okay, right. Since A is contained in union of Gik, I can say that it is also contained in this intersection Y, okay, I will write it separately because this will confuse, okay. Since A is contained in Y, okay, I will continue there. Since A is also contained in Y and A is also contained in this, A is contained in the intersection of this and Y, okay, right. So A is contained in union of Gik, K going from 1 to n, intersection Y. Okay, now it is an elementary set theory that this is the thing but union of Gik intersection Y, okay, that is this right hand side is the thing but union K going from 1 to n Gik intersection Y, okay, and what we have seen here is that for each index I, Y intersection Gi is nothing but Hi, okay, so Gik intersection Y is nothing but Hik, okay, so this is the thing but union K going from 1 to n Hik, okay. In other words, this last what we have put is A is contained in union of Hik, K going from 1 to n, so that means that is this Hi1, Hi2 etc. Hin covers A, okay. So again remember, starting from this open cover of A, we have produced a finite subcover. Remember that is important, this Hi1, Hi2 those are sets from the same cover which cover A, okay. So that shows that every open cover of A in Y has a finite subcover, so that shows that A is compact in Y, okay, that shows that A is compact in Y, okay, is it clear? Okay. Now how to go the other way? Other way you start with assuming that A is compact in Y, okay, that is even easy. So suppose A is compact in Y, then we want to say A is compact in X, okay. To start to show that A is compact in X, we should start from some open cover of A in X. So let us say that let us say Gi, I belonging to I, be an open cover of A in X, okay. Again let me remind you, this means that A is contained in union of Gi, okay, and okay let me write, that is A is contained in union of Gi, I belonging to I, and each Gi is open in X, okay. But if Gi is open in X, if we take its intersection with Y, that will be open in Y, okay. So each Gi is open in X, this will imply that Gi intersection Y is open in Y, okay. Basically in a certain sense we are reversing the steps, okay. So not exactly, each, so Gi intersection Y is open in Y, so suppose I call that set as Hi, okay, Hi as Gi intersection Y, okay. Then what we can say is that since A is contained in union Gi and A is also contained in Y, that will give that A is contained in union GI intersection Y, okay, which is same as saying that A is contained in union HI, okay, that is union HI, I belonging to I, okay. Alright, I will continue the proof here. So this last thing is same as saying that this HI is an open cover of A, okay, this HI is an open cover of A in Y, okay, that is this HI, I belonging to I is an open cover of A in Y, okay, and we have assumed that A is compact in Y, okay, we assume that A is compact, so hence it has a finite subcover, okay, and hence has a finite subcover. Suppose I call that finite subcover HI1, HI2, etc. Okay, so it has a HI1, etc. HIN. Okay, then that means that is A is contained in union HIK, K going from 1 to N. Okay, but now we can say that each HI is GI intersection Y, okay, each HI is GI intersection Y, so we can say that each HI is contained in GI, okay, each HI is contained in GI, so I can say that this is contained in union GIK, K going from 1 to N, okay, but this last thing means that GI1, GI2, GIN covers A, and that is a finite subcover of this GI I going to I, okay. So again we started with an open cover of A in X and we produced a finite subcover of that, so that shows that A is compact in X, okay. So starting from the assumption that A is compact in Y, we have now proved that A is compact in X, okay, is that clear? So now we have proved it both ways. So if A is a subset of Y, then saying that A is compact in Y and A is compact in X, these two things are the same, okay, there is no difference in this, okay. So that is why now here afterwards when we talk of a subset A of X, without bothering about what X is, we can simply say that A is a compact set, okay, and also we can simply now talk about X as a compact metric space, okay. Let me again remind, X as a compact metric space makes sense, but X as an open metric space or X as a closed metric space does not make any sense, right, okay. Now let us also see some properties of compact metric space, so that that helps us in recognizing which sets are compact in, for example let us say we want to know which subsets of real line are compact, okay. Of course we already know, till now we know that all finite subsets are compact. To know what are the other sets that are compact, if we show that every compact set must produce some property, then if we come across a set which does not have that property, we can certainly say that that set is not compact, okay. Alright, okay. So to that extent let me just prove one following theorem, okay. Let XD be a metric space what we shall prove is that every compact set must be closed, okay, every compact set must be closed, okay. So if A contained in X is compact, then A is closed in X, that is if A is compact in X, then A is closed in X, okay. What is the use of this theorem? that suppose we come across a set which is not closed, we can certainly say that it is not compact, okay, right. For example, we can say that for example, suppose I take this interval 0 to 1 as a subset of R, okay, over interval 0 to 1, then we know that this is not closed, okay, and hence by this theorem it is not compact, okay. So we can though this doesn't tell us still which are the compact sets, it certainly says which are not compact sets, okay. So if a set is not closed, we can immediately conclude that it cannot be a compact set, okay. All right, that is after proving this theorem, but anyway that theorem we shall prove now, okay. Okay, suppose A is compact, okay. All right, we want to show that A is closed, okay, we want to show that A is closed, okay. Is it same as showing that X minus A is open? We have seen that to say that a set is closed is same as saying that its complement is open. So we shall show that, we shall show X minus A is open. Okay. So how does one show that something is open? If you take any point in this, we should show that is an interior point, that is if you take any point in it, we should show that there exists an open ball with center at that point which is contained in it, okay. So suppose I call that point as P, okay, let us say let P belong to X minus A, then we should find some positive number, let us say R, such that open ball with center at P and radius R is completely inside X minus A, okay. If we can prove that, that will mean that X minus A is open, and it will mean that A is closed, okay. All right, okay. Now we will proceed as follows. So consider some small a in A, okay. Then what we know is that, okay, let me I think draw some picture so that may be clear, okay. So suppose this is the set A and this is the point P which is outside A, okay, which is outside A, okay? And A is a point in A, small a is a point in A, okay. What I can do is that I can consider open balls with center at A and center at P, okay, such that they are disjoint, such that can be always done. And what is the way of doing that? We can take the radius of each of these balls less than half of the distance between A and P, okay. So that actually does not matter what radius I take. So what I can say is that I can always consider a subset, two open balls with center at A and center at P such that they are disjoint, okay, they are disjoint, okay. So and let me give some notation. Suppose I call, let us say U P, sorry, let us say U suffix A as an open ball with center at A, and let us say radius R suffix A, let us say radius R suffix A, and suppose V suffix A as an open ball with radius P, sorry, center at P, that is U open ball with center at P and radius R suffix P, not R suffix P, okay. Let me call that also as R suffix A, okay, okay. And what is R suffix A? R suffix A is some number that I want to choose in such a way that UA intersection VA should be empty, okay. I want to choose the number R suffix A in such a way that the intersection UA and VA is empty. So how should that number be chosen? It can be chosen, that is all that we need is that this is a ball, this is the radius R suffix A, and this is the radius here, this is also R suffix A, okay, okay. So if I choose r suffix a in such a way that 2 times r suffix a is less than distance between a and p, then this will happen, okay. That is, you choose any number r say such that 0 less than r suffix a less than 2 times the distance between a and p. That is clear, okay. So let us again recall, that is what we have done. We have taken any point p in x minus a and take any small a in a, then choose a number r a which is strictly less than 2, which is positive and strictly less than 2 times distance between a and p. Then let u suffix a as u a r a, v suffix a as u p r a, okay, right, okay, alright. Now consider this family u suffix a belongs to a, that is an open cover of a, okay, is an open cover of a. Okay, obviously each of this is an open set because it is an open ball, okay, and why it is an open cover of a, because a belongs to u a, okay, a belongs to u and we are taking all a in a, okay, right? Okay, so this is obviously an open cover of a, and since a is compact it should have a finite subcover, okay, and hence has a finite subcover, has a finite subcover. Suppose that finite subcover is say u a1, u a2, etc., u a n, okay, right. So that means a is contained in u a1 union u a2 union u a n, okay, alright. Now consider the corresponding sets v a1, v a2, v a n, okay, and consider their intersection, okay. So let us say that let v be intersection of v let us say v a k going from 1 to n, okay, right. Then since v a1 intersection u a1 is empty, v intersection u a1 is empty, okay, etc., okay. So in other words what I want to say is that v, in fact what I will say is that then v intersection a is empty, okay, v intersection a is empty. Why v intersection a is empty? Because v intersection u a1 u a, etc., everything is empty, okay, and a is contained in their union, okay, a is contained in their union, okay. So v intersection a is empty, but v intersection a is empty is same as saying that v is contained in x minus a, okay, v intersection a is empty, this means v is contained in x minus a, okay, alright. But is v an open ball? Okay, it is an intersection of a finite number of open balls, okay, so it is an open. So in fact if you take the radius is the minimum of r a1, r a2, r a n, okay, that is nothing but the open ball with center at p and radius that whatever is that number minimum, okay. So this is an open ball which is completely contained in x minus a with the center at p, so that shows that x minus a is open, okay, that shows that x minus a is open, okay. So what did we show? That every compact set is closed, okay, every compact set is closed. So in particular you can say that if you come across a set which is not closed, then that set cannot be compact, right, okay. Now I shall just give you an exercise. We have just now seen that this set 0 1 is not closed, okay, and hence it is not compact, okay, alright. So if a set is not compact, by definition what should happen? For a compact set we mean that every open cover must have a finite subcover, If a set is not compact, what should happen? There should exist some open cover, right, which does not have a finite subcover. Now this set is not compact, okay, so this should have some open cover which does not have a finite subcover, right. So that is an exercise, okay. Exercise is this: find an open cover of 0 to 1 that does not have a finite subcover, that does not have a finite subcover. Okay. Okay. Next we shall show that the image of a compact set under a continuous function is always compact, okay. We had done similar thing in case of connected sets, okay. We had shown that image of a connected set under a continuous function is connected. Similarly, we will show that image of a compact set under a continuous function is compact. So to do that, we need to consider two matrix spaces. Let xd and y rho be matrix spaces, and f from x to y be continuous. That is, we are considering two matrix spaces and a continuous function from one matrix space to other matrix space, okay. And what we want to say is that if we take a subset A of x and if that subset is compact, then f of A is compact in Y, okay. So if A is a subset of x is compact in x, then f of A is compact in Y. Inwards, the image of a compact set under a continuous function is compact, okay. Usually it is expressed by saying that a continuous image of a compact set is compact, okay. Alright, okay. We want to show that f of A is compact in Y, okay. Alright, so by definition what does it mean? We have to show that if you consider an open cover of f of A, then it has a finite subcover, okay. So let us say that let Gi I belonging to I be an open cover of f of A in Y. What does it mean? It means two things: each Gi is open in Y, okay, right, that is, let me write it in full form, that is each Gi is open in Y and f of A is contained in union Gi, okay. Alright, but till now we have not used the fact that f is continuous, okay. But we have proved earlier that if f is continuous, then the inverse image of an open set is open, okay. So if each Gi is open, it follows from this that f inverse Gi is open in X, okay, right. alright. Now f of A is contained in union Gi, okay. So this means that A is contained in f inverse Gi, okay, right. A is contained union of f inverse Gi. So this last thing will imply that A is contained in union f inverse Gi okay, and each of this set f inverse Gi is an open set in X, okay. In other words, what you have here is an open cover of A in X, okay, right. But we have assumed that A is compact in X, okay. So this open cover must have a finite subcover, this open cover must have a finite subcover, alright. But that means what? That means there should exist some finite number of indices, let us say 1, 2, etc. k, such that A is contained in union of f inverse G1, f inverse Gi1, f inverse Gi2, etc. okay. So since A is compact, there exists, let us say, indices I1, I2, let us say In in I, such that A is contained in union f inverse G, let us say Gik, k going from 1 to n, okay, alright. But then what can we say about f of A? F of A must contained in union of Gik, k going from 1 to n, then f of A must be contained in union of Gik, k going from 1 to n, okay. Now does this prove whatever we wanted? Okay, we started with an open cover of f of A, okay, and now we have produced a finite subcover of that, okay. So this shows that every open cover of f of A has a finite subcover, okay, and that is same as saying that f of A is compact, right. Okay. So what we have proved, that a continuous image of a compact set is compact, okay. Okay, let us also prove one more thing, that suppose you take a compact set, okay, and if you take a closed subset of that, then that should also be compact, okay, right. So that is a theorem, okay. Suppose XD is a metric space, and let us say A is a subset of X is compact, okay, and suppose B is a subset of A, suppose B is a subset of A and B is closed, okay. Of course here this is slightly vague, okay. By B is closed, what do we mean? Whether B is closed in A or B is closed in X, okay. We shall show that does not matter very much, okay. In both cases we can show that B is compact, okay, then B is compact, okay. In other words, a closed subset of a compact set is again compact, okay. Okay, now to prove this, okay, alright, since we do not have much time, I will just give you an idea how we are going to prove this, okay. To show that B is compact, what we need to show is that every open cover of B has a finite subcover, okay. We know that A has that property, okay. So the obvious idea should be to construct, if you start from an open cover, take any open cover of B, from that if we can construct a cover of A and then use the compactness of A, okay, that is an idea, okay, that is start from an open cover of A, sorry, start from an open cover of B, okay, and from an open cover of B construct an open cover of A, then using the compactness of A, that open cover of A will have a finite subcover, okay, then come back to, from that finite subcover construct a finite subcover of B, that is the idea, okay. We shall see how exactly that idea is to be applied in the next class. Okay.